In this video, we're going to talk about net force. Remember that force is a vector, and if I want, I can take multiple force vectors and sum them together. That's what the net is. So we put a sigma in front of F to remind us that this is the net, or the sum, of all the force vectors, and it's going to be however many force vectors we have. Maybe 1, 2, 3, who knows? That's a terrible 3. So that's what the net force is. It is its own vector, so we could write or draw an arrow, and the length of that arrow would represent the magnitude of the net force. There would be some angle theta representing its direction, and it would have x and y components. The x component we would call sigma fx, and the y component we would call sigma fy. Now, typical vector math is going to let us find the values for these things. So if I want the magnitude, then I would do the square root of the x component plus the y component, both of them squared. And if I want to find the angle theta, then I can use tangent inverse of the y component over the x component. Now, sometimes it'll be helpful for us to sort of separate the x and the y components. So if I have vectors f1, f2, f3, then I'm probably going to find the sum of their x components by looking at f1x plus f2x plus f3x, like we do with vectors. And the same thing for y, f1y plus f2y plus f3y, which we can get these just by sort of looking at them, or if you remember, we can always write an x and a y chart for all of our vectors to help us organize what those values would be. So let's do an example. 3 forces act on a 10 kilogram object as shown below. Find the magnitude and direction of the net force. Okay, so I'm going to go ahead and make a little chart, x and y, for my vectors f1, f2, and f3. Then I look at what components these vectors have. I see that f1x has, we would call this f1x, so that's 1, 2, 3, 4 for its x component, and it's going right, so positive. And then fy, not sigma, just f1y, goes up 1, 2, 3, 4, so 4 for that component. And I'm going to get rid of these just to help keep everything clean. F2 is only an x component of -2, and it doesn't go up or down, so 0 y component. F3 has no x component because it doesn't go left or right, and it has a -3 y component. So if I sum the x components, I'm going to get 4 plus -2. So 4 plus -2, which is 2. And I can actually put units to these since I know that they're forces, so 2 newtons. And the y component would be 4 plus -3, which is going to give me, I'll write it here just to be consistent, which is going to give me +1 newtons. Okay, so now I can use those components to find the magnitude and direction of my net force. The magnitude of the net force, so like the length of the arrow that represents the net force, is going to be that 2 newtons squared plus the y component, 1 newton squared. So the square root of 2 newtons squared plus 1 newton squared is going to give me 2.23. So we'll say that 2.2 newtons is the net force, the magnitude of the net force. And then the angle, theta, would be tangent inverse of the y component, 1 newton, over the x component, 2 newtons, which tangent of 1/2, the inverse tangent of 1/2 is going to give me 26.56, 26.6 degrees. So if I wanted to graph this, I could pretty easily. I could take the 2 and the 1, right? So over 2 up 1. So this represents the net of those three vectors. And I know that its magnitude is 2.2, and this angle that it makes with the x-axis is 26.6 degrees. Okay, great. So there's nothing really new here. We're just applying what we know about vector sums to the idea of multiple forces. In this case, I don't know what they are, but I know there are three of them. Now, the reason we want to know what the net force is, sigma F, is because only the acceleration of an object can be known from the net of all the forces. So this is a really big, important equation for us. Write it somewhere and write it somewhere big. Acceleration is equal to only the net force divided by mass. Of course, we can rewrite this different ways. We could say F equals m times a, and we could also say that m equals net force over acceleration. So that's just the different ways that we could rewrite this. But it's important to know you can only relate acceleration to force if it is the net force. Before we were only dealing with one force, so now we're dealing with multiple forces, and it's important for us to take their net if we want to find the acceleration. The units are the same, newtons of force, accelerations, meters per second squared. Let's see how this works with the problem that we just did. So if you remember, our net force that we found is over 2 up 1, which I'll redraw here. That's our net force. The magnitude was 2.2 newtons. I'm sorry, take the arrow away from magnitude. And the angle was 26.6 degrees. So if I want to find the acceleration, all I need to do is take that net force and then divide it by the mass of the object, which is given to us here. So 2.2 newtons divided by 10 kilograms. Remember, a newton is really a kilogram times a meter per second squared. So the kilograms cancel out. And 2.2 over 10 is going to give you 0.22 meters per second squared. Now, here's the thing. That is the magnitude of the acceleration. What about the direction of the acceleration? Well, the acceleration and the force, if you remember from Newton's second law, they're in the same direction. When you punch someone in the face with a force, the acceleration of the change of motion is proportional and in the same direction as that force. So the angle for the acceleration is 26.6 degrees. If I wanted to write that maybe in vector notation, then I could say 0.22 meters per second squared for the magnitude, comma, 26.6 degrees for the angle. And if I wanted to draw this, it would be in the exact same direction. So it would point along the net force. It would just be a little bit smaller because 0.22 is smaller than 2.2. All right, let's do another problem. Three forces act on a 10 kilogram object as shown below. Find the magnitude and direction of the acceleration. Okay, well, so here again, I might make an X and a Y chart to separate my F1, F2, F3, and F4. And if you can do this pretty easily, you don't have to write out this chart. You can just go ahead and skip to the sum of the X and the sum of the Y if you feel like you can see it without the chart. So F1 goes over 1, 2, 3, 4, so the X component is 4 newtons, and the Y component goes down 1, so negative 1. F2 has no X component because it points up, and it points up 1, 2, 3, 4, so 4 newtons is the Y component. F3 doesn't point up or down, so its Y component is 0, and it goes to the left, 1, 2, 3, 4, so negative 4 is the X component. And for the fourth force, it goes down, so there's no X component. 1, 2, 3, so negative 3 newtons of force for that vector. Okay, so I sum the X's, and I've got, let's see, 4 plus 4, so that's, 4 plus negative 4, which is 0, so there's no newtons in the x direction. And then for the y component, I've got negative 1 plus 4 plus negative 3, which is going to give me also 0. Okay, well, that means that the net force is 0. And there's no angle to it because it's basically we're saying there's no net force. It's almost like all of the x components cancel each other out, and all of the y components cancel each other out. So in this situation, that means that the acceleration, which is the net force divided by mass, is going to be 0, because it's 0 divided by 10 kilograms, which is 0. So when the net force is 0, the acceleration is 0. Remember, accelerating is speeding up, slowing down, or changing direction. So what this means, if the net force is 0, is that this object is not speeding up, slowing down, or changing direction. So like turning. Terrible at spelling. Okay. There's actually a special name for this in physics. We call this equilibrium, or when the forces are balanced. So equilibrium is when the net forces are 0. When the net of the forces is 0, then this means that the object is not speeding up, slowing down, or changing direction. It's either at rest or it might be moving with a constant velocity. Either of those two things can happen, okay? It can't speed up, slow down, or change direction, but it might be at rest and it might have constant velocity. Now, sometimes we like to say that the forces are balanced if the x forces are balanced and the y forces are balanced. Like sometimes the left and right forces will be balanced, but the y forces are not. And that just tells us that the acceleration is in the y direction. Let's do another problem. Oh yeah, this is a great equilibrium problem. Two forces act on an object as shown. Find the magnitude and direction of a third force that would put this object in equilibrium. So what would a third force have to be to balance these two forces, right? Which means we want the sum of these forces to be 0. Well, if you can see it, F1, let's make a little chart. X and Y. F1 has no x component and 1, 2, 3, 4 for a y component, positive 4. And F2 has negative 2 for the x component and 0 for the y component. So that tells me that F3 is going to need to have positive 2 for an x component to balance that x force, that negative 2. And the y component is going to be negative 4. So positive 2, 1, 2, and then down 4, 1, 2, 3, 4. So this is what F3 would have to be in order to balance those two forces, because now I know the sum is going to be 0. To get the magnitude of that force, I use its components, not the net, the magnitude of F3. Then I would do the x component, 2 newtons squared, plus negative 4 newtons squared, and the square root of 2 squared plus negative 4 squared is a number, it's 4.47, we'll say 4.5 newtons. And the angle, which we can call theta 3 if we want, is tangent inverse of negative 4 newtons over 2 newtons. Tangent inverse of negative 4 divided by 2 is going to give me negative 63.4 degrees. And this angle is in the fourth quadrant, right? 1, 2, 3, 4. And tangent inverse does give me correct angles in the fourth quadrant. The negative just means that it's going below the x-axis instead of above. Okay, great. Now let's talk about free body diagrams. So basically, a free body diagram is just what we've been doing by looking at the forces on an x and y graph. Only sometimes we don't have an x and y graph written for us, and we have to make up our own graphical representation of the forces. So let's do this one. 4 forces are applied to a 0.5 kilogram soccer ball. A 10 Newton force north, a 12 Newton force east, an 8 Newton force south, and a 4 Newton force west. Draw a free body diagram of this picture. So basically, a free body diagram is when you only imagine the one object that you're focusing on, which for us is the soccer ball. And if you want, you can draw a soccer ball. I'm really bad at drawing hexagons. Or instead, if you don't want to, you can just draw a dot. And that dot represents the center of mass of the soccer ball. Then we draw all of these forces coming out of the dot. So the 10 Newton force north is up, so we would say that that force goes like this. It comes up, out. And if I want, let's call this F1. Okay. A 12 Newton force east, remember, never eat soggy wontons. East is to the right, so that 12 Newton force is going to go to the east, and it'll be slightly bigger than F1 because F2. 12 is bigger than 10. All right, now an 8 Newton force south, we'll call that F3. An 8 Newton force south would go down, and it'll be slightly smaller than F1 because 8 is less than 10. And then the last one, a 4 Newton force west. That's the smallest one. We'll call this F4. Okay, great. So that's our free body diagram. It's really simple. B, find the magnitude and direction of the net force and acceleration. Okay, well, now I could draw a chart for this, but every single force is either an X or a Y force. So let's see if we can do this without the chart. Fx and Fy. Okay, let's start with F1. F1 points up, and it's 10 newtons up. So that's going to be a Y force, and it will be a positive 10 newtons of Y force. F2 points to the right, so it's positive, and it's going right, so that's going to be an X force. F3 points down, and it is 8 newtons of force, so that's a Y force, and we would make it negative. And F4, 4 newtons of force west, so that's going to be an X force, and it goes in the negative or left direction. Okay, so the sum of the X component, or sorry, not components, X forces is going to be 12 minus 4, or 8. And the sum of the Y forces is 10 minus 8, or 2. Now I can find the net of these forces. The net of these forces, the magnitude of the net force is the square root of the X component, so 8 newtons, right? That's what this is, squared, plus the Y component, squared. That's this. So the square root of 8 squared plus 2 squared is 8.24, so we'll say 8.2. That's the magnitude of the net force. And the angle, tangent inverse, is going to be 2 newtons over 8 newtons. And the inverse tangent of 2 over 8 is 14.03, so we'll say 14.0 degrees. So there we go. That's the magnitude and the direction of the net force. Now to get the acceleration, remember that acceleration is net force over the mass. So if I want to find the magnitude of the acceleration, I just take that 8.2 newtons and divide by the mass of 0.5 kilograms. 8.2 divided by 0.5 is 16.4 meters per second squared. So that's the magnitude of the acceleration. What about the angle of the acceleration? Well, hopefully you remembered that the angle of the net force, which is 14 degrees, is also the angle of the acceleration. Because again, Newton's second law says that the force and the change of motion resulting are in the same direction. Okay, great. Now, notice that I didn't draw the net force on the free body diagram. That's because you typically don't draw the net force on the free body diagram. Instead, if you need to, you can just draw it on a new dot representing the objects of the soccer ball. And this is 8.2, so it looks something like that, 14 degrees. You can always use that information to draw the net force for you, but you typically do not include it on the free body diagram. Also, it's important to know that the arrows of the free body diagram, they touch the dot. That's always an important thing to do. This video is done.